Hello, everyone. My name is Yang Liu. Today, let's explore the fascinating world of trigonometry by diving into its history, practical applications, and artistic beauty. Have you ever wondered about the angle of the Leaning Tower of Pisa's tilt? With the help of trigonometry, we can solve such mysteries. Today, our focus will be on trigonometry's history, its functions and graphs, and its artistic expressions. To start, let's delve into the origins and evolution of trigonometry. Trigonometry originated in ancient Egypt and Babylon for practical geometry. Hipparchus introduced the first trigonometric table, Aryabhata refined sine functions, and Islamic scholars advanced tangent functions. By the 15th century, Europe applied it to navigation and astronomy, and Euler in the 18th century defined its modern form, making it a universal mathematical language. Now, let's explore the second section, the functions and their graphs. For precise visualization, I created all the diagrams in this presentation using GeoGebra. First, let's take a look at the definitions of sine and cosine. These fundamental trigonometric functions are derived from the relationships within a right-angled triangle. Sine is defined as the ratio of the length of the side opposite the angle to the hypotenuse, while cosine is the ratio of the length of the adjacent side to the hypotenuse. These definitions not only form the basis of trigonometry, but also play a vital role in describing circular and periodic phenomena. Building on the sine and cosine definitions in a right-angled triangle, we extend this to the unit circle. Here, a right triangle with radius 1 allows us to define point B's coordinates as cosine theta and sine theta. If point B moves dynamically, its coordinate formula remains unchanged. Additionally, using the definition of a circle, we derive cosine squared theta plus sine squared theta equals r squared, which equals 1. Next, we plot trigonometric functions to visualize how x and y vary. We can observe that the period of the trigonometric functions corresponds to a full circle, which is 2 pi. By observing the wave-like patterns of sine and cosine, we can see how they mirror the circular motion, providing a clear and intuitive connection between the unit circle and the behavior of trigonometric functions. Additionally, we can identify some special angles from the graph. These angles, such as 0, pi over 6, pi over 4, pi over 3, and pi over 2, correspond to specific points on the unit circle and have well-defined sine and cosine values. From the sine and cosine graphs, we can clearly observe that both functions exhibit a maximum value of 1 and a minimum value of -1. Using the visuals, we also derive key identities. Moreover, we explore other important trigonometric identities. Understanding these relationships deepens our comprehension of how these functions behave and interact. Let's examine two variations of the sine function to understand how changes to its parameters affect its behavior. The first variation completes one period in a shorter time, indicating a higher frequency and thus more cycles within the same interval. This means the wave oscillates more quickly compared to the standard sine function. The second variation displays a wave with an amplitude that is doubled. This results in peaks that reach twice as high and troughs that go twice as low, demonstrating how changes in amplitude stretch the wave vertically. Similarly, the same principles apply to variations of the cosine function. By adjusting its parameters, we observe changes in amplitude and frequency, just as with the sine function. To conclude, the parameter A controls the amplitude, while B dictates the frequency. Together, these parameters shape the behavior of the trigonometric function, allowing for diverse and dynamic applications in mathematics and real-world modeling. In addition to sine and cosine functions, there are other common trigonometric functions that can be derived from them. Now, let's revisit the Leaning Tower of Pisa. By applying trigonometric principles, we analyze the relationship between the tower's height and its displacement at the top. With a height of approximately 54.5 meters and a horizontal shift of 5.2 meters, we calculated the sine of the tilt angle as the ratio of these two values. From this, we derive the angle of tilt to be nearly 5.5 degrees, demonstrating how trigonometry provides a precise way to measure and understand real-world phenomena. Trigonometric functions play a crucial role in astronomy, especially in calculating celestial distances and positions. Using formulas like the cosine rule, we determine angular heights, while the parallax distance formula allows us to measure the distance to nearby stars. Additionally, the orbital mechanics formula describes the elliptical orbits of planets. These equations highlight how trigonometry helps us explore and understand the universe's vast structure. Next, we transition to an exciting section exploring the artistic side of trigonometry. Before we begin, let's introduce a concept. This is the Cartesian coordinate system, the most commonly used one. But are there other coordinate systems? The answer is yes. One such system is the polar coordinate system. Polar coordinates have a rich history, from Apollonius and Ptolemy, describing celestial paths to Newton's application in orbital mechanics. Euler formalized them in the 18th century, linking polar and Cartesian coordinates with key equations. This made polar coordinates essential in geometry, physics, and engineering. In the Cartesian coordinate system, coordinate xy can be converted into polar coordinates as r, theta, which is particularly useful for rotational patterns. Let's examine the parametric polar rose, a captivating curve that merges mathematical precision with natural beauty. Its graceful symmetry and periodic structure symbolize patterns found in nature, like blooming petals or rippling waves. In polar coordinate, the formula r of theta equals sine of k times theta can be converted into Cartesian coordinates, enabling visualization in 2D space. As theta varies from 0 to 50 pi, the curve's periodicity and complexity unfold. The parameter k determines the number and shape of petals. Integer k produces 2k symmetrical petals, while fractional or irrational k results in non-closing, intricate patterns. This interaction between sine and cosine mirrors natural symmetry, like flower petals. Its periodicity not only holds aesthetic value, but also has practical uses in analyzing waveforms and vibrations, describing phenomena like mechanical oscillations, light, and sound. Additionally, parametric formulas like this are widely used in computer graphics for creating visually striking animations. The parametric polar rose graph visually represents signal periodicity and symmetry. In AM signals, pedal changes reveal frequency shifts, while in FM, pedal numbers indicate modulation depth. In 5G networks, MIMO antennas utilize high directionality to reduce interference. Adjusting the rose graph's parameters helps visualize the distribution of multi-directional beams, assisting in antenna design. In conclusion, we explored trigonometric functions and the parametric polar rose, examining their historical roots, concepts, and real-world applications. Remember the beauty found in the study of the math? Exploring these curves enhances our grasp of mathematical concepts and reveals the elegant connection between math and nature. This interdisciplinary view offers a new appreciation of the harmony between mathematics and the natural world.